Hello, chemistry. Today we are going to be talking about matter and physical properties. We will be getting into some chemical properties and looking at the composition of matter as we move forward this week. But today we are focusing on physical properties. We've discussed this briefly in class, but I want to make sure we have a solid understanding of what matter is and how that breaks down into different groups. And to start that conversation, we are going to talk about anything that is considered a substance. So a substance is matter that has uniform and definite composition. They're sometimes referred to as pure substances. However, I find that to be a little bit redundant because if something is a substance, it's already clearly defined as having uniform and definite composition. But this is just language that is somewhat common. For something to be uniform, it means it is the same throughout. So if you take any portion of a sample, it is going to be the same composition. Definite means it's defined. Table salt will be made of sodium and chlorine atoms. And so any sample of table salt that we take and investigate is going to be specifically defined as that. Any sample of copper that we look at will be composed of copper atoms. So anything that is uniform and definite in its composition is considered a substance. So there's only one type of matter in a substance. We can have elements, like I described the samples of copper. They will be made of only atoms of copper. Compounds are made up of more than one type of element, but they are consistent throughout. All samples of a substance have identical physical properties. So no matter if we're talking about the Statue of Liberty in terms of copper or a penny, right? They will have the same physical properties. And we're going to get to physical properties just a little bit down the road in this lecture. I'll give you some examples of what physical properties can be. So we need to be able to recognize what is a substance as opposed to being a mixture, and then think about how properties are consistent across a substance. We can break down types of properties a few different ways. One of the ways that I want to be able to do this is thinking about extensive properties versus intensive properties. Also in this course, we're going to be thinking about physical properties versus chemical properties. But right now, let's take a look at extensive and intensive properties. An extensive property is simply a property that depends on the amount of matter in a sample. So this is a property that is really a function of how much of the matter is there. So if we think about mass, right, the more of a substance that is there, the higher the mass of that sample will be. Same thing with volume. If we have more water in a sample, it will have a higher volume. An intensive property, conversely, does not depend on the amount. It only depends on the type of matter in the sample. Density is a really nice example of this. And density is, of course, calculated from the mass and volume of a sample. So density of an element or any substance is going to be the same no matter how much of the substance there is, assuming the other conditions are the same. Color is another example. Color will stay the same. I think a really interesting example of thinking about extensive versus intensive properties is heat capacity versus specific heat capacity. Later on in the year, we will get to some experiments and calculations working with heat capacity and specific heat capacity, but we'll just kind of talk through them here. Heat capacity is defined as the amount of energy to raise the temperature of something 1 degree Celsius. So this could be a penny or the Statue of Liberty. It's the amount of energy required to raise something 1 degree Celsius. Now, hopefully, intuitively, you recognize that the amount of energy required to raise the Statue of Liberty by 1 degree Celsius is going to be significantly higher than that of a penny, even though they're both made of copper. So that is an extensive property. It depends on the amount of matter. Specific heat capacity, on the other hand, is defined as the amount of energy required to raise 1 gram of something 1 degree Celsius. This is an intensive property because anything made out of copper is going to have the same value, no matter how big it is. And that's because it's normalized across the mass. Okay, so one of the main points of this particular lecture is for us to get a good understanding of what a physical property is. So a physical property is a quality or condition of a substance that can be observed or measured without changing the substance's composition. Here are some examples: color, solubility, odor, density, melting point. So with each of these, we can take a sample of a substance and we can determine these things. What color is it? Does it dissolve in water? We can calculate its density through measurement, or calculate or measure its melting point. And we can observe each of these traits without changing the identity of the substance. Okay? And this is diverging from what we'll learn is a chemical property down the line. So the key to this is whatever substance we're looking at is the same thing before and after we observe these properties. Suppose we are finding the density of some PVC, some polyvinyl chloride. We can find the volume, we can find the mass of our sample, and calculate the density, right? In doing so, it's still PVC, both after we've made those observations, the same as it was before that. If we want to determine the melting point of water, we can lower a sample until it starts to freeze at 0 degrees Celsius. And even though it has changed state, it is still water, right? Whether it's liquid or solid. So a physical property, again, just to reiterate, is any property where we can observe it without changing the identity of the substance. Physical changes really follow in this line of thinking. When we cause a physical change to happen or observe a physical change, we are noting that matter changes in a way that does not affect the chemical composition. So something could be cut. If we take a piece of paper and cut it into several smaller pieces, yes, the shape of those pieces have changed. The size of each individual piece has changed, but it is still paper. The chemical composition has not changed. If we grind something down, again, it's causing it to be changed into many small pieces, but it is not changing the substance. Bending a piece of metal, it is still the same substance. And melting. This is one where I talked about it briefly on the previous slide, but can catch students sometimes. Changes of state are physical changes. So when something melts or boils or freezes, right, or condenses, this is a physical change because after the change of state, the substance is still the same, has the same identity as before. When we boil water and water goes from a liquid to steam, they are still H2O molecules. The chemical identity of the substance has not changed. Okay, so I'm going to give a few instructions here, and then I would like you to pause the video and try and fill this chart in on your own. I think that much of this is intuitive to our understanding of the world. However, I want you to try and go through this as best you can, and then you can unpause the video and come back and we'll share how we think about this. Before you do that, I want to help with language a little bit. When we think about shape and volume for states of matter, I like to use the language definite and indefinite, where definite means it's kind of predetermined regardless of the container that it's in or what it's being held in. And indefinite means that it would take either the shape or the volume of the container as it's being moved from one holding space to another. For expansion on heating and compressibility, we can say yes or no. Sometimes we get a little more specific and say very minor, or it does expand a great deal. So go ahead and pause and try and fill in this chart. Okay, welcome back. So we're going to go through these and, like I said, point out some language that you might not have used intuitively but should match up with how we should think about these. So I want to take a look at solids to get started. The shape of a solid is definite. The atoms are arranged in a stable way where they are staying in the same position relative to one another. Right? So the shape of a solid does not change no matter what type of container we put it into. The atoms or molecules are not moving around each other. Likewise, since those fundamental units are not moving around, they're also not getting closer or further apart from each other based on the container it's being held in. So both the shape and the volume are definite. Solids will generally expand slightly on heating. This can play a really important role in some engineering, but for the purposes in this class, most of them won't change much in a measurable way for us. And then compressibility, as I just referenced, the atoms and molecules in a solid are so close together already, we can't really compress them into a smaller space. So we will say it is incompressible. For a liquid, the shape of a liquid changes depending upon the container that it's in. So if it's in a cylinder, it will take the shape of a cylinder, and then if we pour it into a box, it will take a cubic shape of the box. So the shape of a liquid is indefinite, and that's because the atoms and molecules are able to move freely. So they are moving around freely. Now, they're still really close together in a liquid. There's not a lot of extra space between the atomic sized particles, whether molecules or atoms. So their volume is definite. They're not spreading out or getting close together. The volume of liquids does change a little bit based on temperature, but again, this is a very slight effect. So they don't expand a great deal on heating. And as the molecules and atoms are quite close together, they are incompressible. And this is really important. A nice example of this is in the vehicles that we drive. Brake lines have brake fluid in them. So if you think about brake lines in a car, you push on the brake pedal in your car and it applies pressure to one end of a line that has brake fluid in it. And that causes that pressure to be transferred down to where the calipers are for your brakes and slows you down as the brakes on the calipers squeeze on the rotors in your tires. Now, if you've ever changed brakes on your own, you know that you have to get all of the bubbles of gas, the air bubbles, out of your brake lines. Because if there are air bubbles in your brake lines, gas is compressible. I say it's readily compressible. It's maybe a little bit hard to see behind my video image there. But gas is readily compressible. So if there are air bubbles in your brake lines, what happens when you press on the brake pedal is it applies the pressure on one end. And if it were all liquid, that pressure is fully transferred down to your calipers. But if there are air bubbles, they do get squished because gas particles have lots of distance in between them and other gas particles. So there's lots of empty space in a gas. This leads to the properties that we see on the table here. The shape of a gas is indefinite. Since the particles are moving freely, they spread out for whatever container they're in. This also means that their volume is indefinite. They will move in random motion, filling up whatever container they're being held in. And if we heat a gas and it has space to move, the expansion will be great. So just to help out, because I think two of these boxes are behind my little face there, gas will greatly expand upon heating, and it is readily compressible when pressure is applied. So we established what substances are, anything that has uniform and definite composition, and now we need to talk through mixtures. So a mixture is a physical blend of two or more substances, and that is a key word. It is a physical blend of two or more substances. It is not a chemical combination or a chemical blend, but a physical blend, meaning each of the substances in the mixture has the same chemical identity before and after the mixture are made. In a mixture, composition can vary. If we think about salt in water, that is a mixture. And there can be a little bit of salt in water, and there can be a lot of salt in the water, right? So it's not predetermined or predefined what the composition is. We will break mixtures down into two different categories. And it's really important that we have a fundamental understanding what these two categories are and how we can recognize and define them. The first is a heterogeneous mixture. In a heterogeneous mixture, the composition is not uniform, right? So if you take two different samples from the mixture, you are certainly not guaranteed and not even likely to get the same composition from each of those samples. it's going to be inconsistent throughout the mixture. So the composition is not uniform. A phase is an important concept for us to think about here. There are multiple phases in mixtures. A phase within a mixture is anything that does have uniform composition. So examples of heterogeneous mixtures, and then I'll point out the phases in each of them. A salad, right? If we just think about a salad, and this is, we're taking a few liberties with this, but in a salad you have lettuce, you have tomatoes, you have cheese, you have dressing, and you have croutons, right? Each of those individual ingredients would be considered its own phase. And again, this is just a little bit of a stretch, but I think it's easier to grapple with when we use an example like a salad. Right? The lettuce has uniform composition within itself. The tomatoes have uniform composition, right? So each of those individual components has uniform composition. Chicken noodle soup. So there's the chicken, the broth, the carrots, and the noodles. Each of those four individual components is a phase. Okay, a homogeneous mixture has only one phase, and that's how we define a homogeneous mixture. It has uniform composition. It has uniform composition, which means that a homogeneous mixture, if you take two different samples from it, should be the same. So there's only one phase in a homogeneous mixture. So I've got some examples on the next slide, but we often refer to these as a solution. So a homogeneous mixture is also known as a solution. The most common solutions that we think about are when we have something dissolved in water. And we'll be talking about those a lot in chemistry this year. But there are a number of different ways that we can think about these. Let's jump to this. All right. So here are 6 different situations where we look at different states of matter being involved in a homogeneous mixture, or a solution if we want to use that language. So in a gas-gas mixture that is homogeneous, air is a really wonderful example of this. The air that we're breathing right now is about 70% nitrogen, and then around 20% oxygen, and then a handful of other things. So it is one phase as we investigate air. It is fairly uniform in its composition, and that is an example of a gas-gas solution. A liquid gas solution, fog is an example of this, where the liquid is distributed across the gas, in this case, which is the air. Gas in liquid solution is really common. So anytime you drink a soda or a LaCroix, a bubbly water of some sort, there is CO2, carbon dioxide gas, dissolved in the water. And there's a number of chemically interesting things that are going on with this. But until you open the can and the equilibrium starts to kind of stabilize and the CO2 is leaving the water, so especially when it's sealed, the CO2 is dissolved in the water, creating a gas in liquid solution. Liquid in liquid, an example that I like is vinegar. It is acetic acid dissolved in water. Solid in liquid, salt in water. This is one that I think we've talked about talked about already, and is pretty easy for us to visualize. And finally, solid in solid. And this one's a little bit harder to imagine, but it's if we think about any alloy, when we make a combination of different metals in different ratios. They're not chemically changing their identity, but we are getting a new set of properties based on the combination of physical properties. So, for example here, and it's just a little bit behind my picture, is copper in silver. So that is sterling silver. Okay, so here is a quick definition of phase, just to make sure that we get this so you can see it and not just have it from me verbally. A phase is any part of a system with uniform composition. Any part of a system with uniform composition. So again, heterogeneous mixtures have multiple phases, and homogeneous mixtures have just one phase. We need to think about how we can separate mixtures. And I'm not going to be able to give us an exhaustive list of methods for separating mixtures, but I can give you a few ideas, and we will actually implement some of these in class together. You've also probably learned some of these when thinking about middle school science. And if you had to do any projects where you separated different components from something, you likely used some of these. The sludge test is a classic example. So separating mixtures is based on physical properties. We could use magnetism. So if there are iron filings in some sand, we could use a magnet to extract the iron filings. Distillation is the separation of liquids based on boiling points. So if we heat a combination of liquids, and then collect different fractions, meaning a component of it that boils at a lower temperature, we can separate based on boiling point. Filtration, so if we have water and sand combined together, if we pour that through a filter, the water would be able to move through and the sand would stay put. And chromatography. So chromatography separates through a process that you will actually see in class next week. You have to use some agent that is soluble in a solvent, and then we'll use some chromatography paper. So just stay tuned. You'll actually get to use that one, which I think will be easier than us trying to describe it here. I can't do that. That is all of the notes for this one. If you have any questions, make sure to let me know. Cheers.